High-threat volcanoes, Mount Hood, Mount St. Helens, and Mount Rainier.
Volcanologists will tell you to this day that St. Helens remains the most active volcano in our state.
For the first time in over 4 decades, the earth beneath Mount St. Helens is stirring once again. NASA has recently confirmed that magma is actively recharging beneath the infamous stratovolcano, signaling a remarkable development in the region's geological history. The seismic silence that followed the catastrophic eruption of 1980 has given way to subtle but unmistakable signs of subterranean awakening. Deep within the Earth's crust, molten rock is on the move, quietly building pressure and reshaping the geological landscape from below. While the volcano remains outwardly calm, what's happening beneath its surface paints a picture of dynamic change, one that scientists are watching with increasing interest. Before we start, smash the like and subscribe buttons for more updates. Mount St. Helens, located in the Cascade Range of the Pacific Northwest, has always been a focal point of geological scrutiny. Its 1980 eruption left an indelible scar on the region, not only reshaping the mountain itself, but altering surrounding ecosystems and prompting a re-evaluation of volcanic risk across the continental United States. Since then, the volcano has been monitored continuously through a complex web of seismic stations, satellite imaging, GPS arrays, and gas sensors. Over the past several months, that surveillance network began detecting something new: patterns of ground deformation, subtle shifts in elevation, and a faint but persistent increase in deep, low-frequency seismic events. These are the signs of magma accumulating, slow, methodical, and potentially significant. The magma is not rising toward the surface in a dramatic push, but is instead gradually accumulating in reservoirs several miles beneath the crust. This recharge process does not necessarily indicate that an eruption is imminent, but it does confirm that Mount St. Helens is very much alive geologically. The Earth's crust behaves like a breathing organism at these depths, flexing and cracking as magma fills the voids left by previous eruptions. The rock above is slowly but perceptibly being altered, fractured, expanded, and pressurized. This is the quiet phase, the slow inhale before any potential exhale of volcanic activity. And it is during this phase that geologists and volcanologists gain their clearest insights into the life cycles of complex volcanoes. NASA's Earth-observing satellites, particularly those equipped with synthetic aperture radar SAR and thermal infrared imaging, have been instrumental in confirming the subsurface changes. SAR allows for the detection of even minuscule movements in the Earth's surface, revealing a mosaic of deformation across the volcano's flanks. These shifts can be less than a centimeter in magnitude, but are crucial indicators of subterranean processes. Thermal data, while not showing surface heating yet, complements this picture by confirming that the changes are not superficial. There are no wildfires, landslides, or other non-volcanic events that could mimic the readings. Everything points to the inner workings of Mount St. Helens reactivating after decades of dormancy. The implications of this magma recharge are far-reaching. While it is natural for volcanoes to undergo such cycles without necessarily leading to an eruption, the renewed magmatic activity resets the clock for hazard preparedness. For the communities near Mount St. Helens, including those in Washington and Oregon, it introduces a renewed focus on emergency planning, land use regulation, and public awareness. The geological clock doesn't tick to human schedules. It moves in irregular, often inscrutable pulses. But when those pulses accelerate, the scientific community must be ready not only to interpret the data, but to communicate its significance clearly and effectively. Mount St. Helens' magmatic reawakening also has profound scientific value. For researchers, the opportunity to study a volcano during its recharge phase offers a living laboratory to observe the prelude to possible future activity. It is during these early stages that models can be refined, hypotheses tested, and prediction tools sharpened. Understanding how magma moves, where it accumulates, and how it interacts with the surrounding rock is central to advancing the science of volcanology. Unlike sudden eruptions, which offer little warning, a magma recharge phase unfolds over months and years, allowing for careful observation and analysis. Each tremor, each fractional uplift adds another data point to the broader picture of volcanic behavior. At a broader scale, the activity beneath Mount St. Helens reflects the ongoing tectonic forces that shape the Pacific Northwest. The region lies within the Cascadia subduction zone, a massive geological boundary where the Juan de Fuca plate is being forced beneath the North American plate. This subduction is responsible not only for the formation of the Cascade volcanoes, but also for one of the most seismically active areas in North America. Magma generation here is a product of intense pressure and friction. Water and sediments dragged deep into the earth melt the overlying mantle, creating pockets of molten rock that rise slowly toward the surface. Mount St. Helens is merely one expression of this vast and complex system, and its current behavior may reflect broader changes happening along the entire arc. While magma recharge does not guarantee an eruption in the near term, it does mark a transition. The mountain is no longer in a purely post-eruption recovery phase. It has entered a new chapter in its life. This chapter may last for decades, featuring continued magmatic buildup, occasional seismic swarms, and perhaps minor steam or ash emissions. Alternatively, the system could stabilize, with the magma cooling slowly underground. These are the unknowns that make volcanic monitoring both essential and endlessly fascinating. With modern tools and long-term data, scientists are better equipped than ever to interpret these changes, but nature retains its secrets, often revealing them only when the timing suits its rhythm. The recharging of magma beneath Mount St. Helens also revives public memory of the 1980 eruption. For many, that event remains etched vividly in recollection. The massive lateral blast, the ash clouds that darken skies across states, the loss of lives, and the transformation of a landscape. That memory adds emotional weight to any new developments at the volcano. Yet the scientific narrative today is different. In 1980, the understanding of magma systems was far more limited. Today, the integration of satellite imagery, infrasound, deep Earth scanning, and real-time data analytics provides a vastly more detailed picture of what is happening below ground. The ability to detect magma recharge this early is a triumph of technological progress and scientific vigilance. At its core, the story of Mount St. Helens today is one of patience. The Earth moves according to its own logic, and volcanic systems often take centuries to cycle through stages of dormancy and activity. What has shifted in the present era is not necessarily the volcano itself, but humanity's capacity to observe it. The magma recharge process now underway is unfolding in full view of an interconnected network of satellites, sensors, and researchers. That network, like the volcanic system it monitors, is dynamic, continually evolving and improving. The lessons learned here may eventually aid in monitoring other potentially hazardous volcanoes across the globe, from Indonesia to Iceland. From a geological perspective, Mount St. Helens' resurgence is also a reminder that no volcano is ever truly extinct. Even long periods of inactivity do not mean a system has shut down. Magma can reside in deep reservoirs for centuries before making any movement upward. When that movement begins, it may do so quietly, as is the case now. The fact that magma is replenishing at depth suggests that the volcano's plumbing system remains functional, that the pathways carved by earlier eruptions are still viable, and that the conditions for future eruptions remain present. In this light, Mount St. Helens becomes both a warning and a wonder, a place where Earth's inner forces can be studied in real time. The current situation also invites a broader contemplation of humanity's relationship with geologic time. The changes happening beneath Mount St. Helens occur over intervals that dwarf human lifespans. A recharge phase might last years or decades without leading to an eruption, yet each stage offers critical knowledge that builds the foundation for future understanding. Our ability to detect such early signs of magmatic movement is both a scientific achievement and a testament to decades of dedicated research. The silence between eruptions is not emptiness. It is a waiting period filled with meaning, data, and potential. Looking ahead, the task now falls on scientists, emergency planners, and policymakers to work in concert. The goal is not to predict eruptions with pinpoint accuracy, a notoriously difficult challenge, but to understand the evolving state of the volcano with enough clarity to provide timely warnings if necessary. Continued investment in research, technology, and public education is vital. The reawakening of Mount St. Helens does not mean disaster is imminent, but it does mean the volcano deserves attention and respect. It is a complex system alive beneath the surface, capable of both beauty and devastation. As magma continues to gather in the depths, the mountain remains outwardly tranquil. Tourists hike its slopes, wildlife has returned to its flanks, and forests have regrown in the shadow of past destruction. Yet beneath that serenity lies a molten engine, gradually building energy. What lies ahead is uncertain, but it is also a rare opportunity to witness, study, and learn from a volcano that is transitioning once more from rest to renewal. The ground may not be shaking violently, but it is moving, and in the world of volcanology, that movement speaks volumes. The revelation of magma recharging beneath Mount St. Helens has ignited new momentum in the field of volcanology, not because it portends an immediate eruption, but because it opens a fresh window into the mechanics of volcanic renewal. While previous activity focused on surface effects, lava domes, ash plumes, pyroclastic flows, this new phase is all about what cannot be seen. Scientists now find themselves observing an entirely subterranean phenomenon, one that unfolds silently, at incredible depths, and without the dramatic cues that mark an eruptive episode. This underscores a fundamental truth about volcanic systems. Their most transformative moments often begin long before the first visible sign appears. This recharge process has sparked a surge in deep Earth imaging efforts around Mount St. Helens. Instruments such as magnetotelluric sensors and gravity meters are being deployed to refine models of the mountain's interior structure. Magnetotellurics allows scientists to map electrical conductivity changes beneath the volcano, which can indicate the presence of partially molten rock and fluid pathways. Gravity measurements, on the other hand, can detect minuscule shifts in the mass distribution below the surface. By comparing data over time, researchers can track how magma displaces rock and fluid in its ascent. These tools are helping to construct a three-dimensional picture of the recharging system, a model not just of movement, but of intent. One of the more intriguing aspects of the magma recharge is the way it interacts with existing geological features left behind by past eruptions. The 1980 eruption drastically reshaped Mount St. Helens' internal plumbing, collapsing its summit and creating a horseshoe-shaped crater. Within this altered framework, the new magma must navigate a network of fractures, cavities, and cooled rock. These pre-existing structures can either facilitate magma movement or inhibit it, depending on their orientation and composition. Understanding how the new material threads its way through this geological maze is critical to predicting potential surface expressions in the future. There's also renewed attention on volatile gases, primarily water vapor, carbon dioxide, and sulfur dioxide, that rise with the magma as it moves upward. Although no significant gas anomalies have reached the surface yet, scientists are watching for subtle increases that might indicate magma nearing shallower depths. These gases play a pivotal role in volcanic activity. As pressure drops closer to the surface, they begin to exhalve from the magma, forming bubbles that can dramatically increase internal pressure. A sudden accumulation of gas in a confined space can trigger explosive eruptions. For now, gas emissions remain within normal ranges, but that could change quickly if the magma continues its ascent. The importance of such monitoring extends beyond Mount St. Helens itself. It offers a case study that may be applied to dozens of similar stratovolcanoes around the world. The mechanisms of magma recharge observed here could help decode the pre-eruptive behavior of volcanoes in Japan, Chile, and Indonesia, regions where millions live within the shadow of active cones. By refining our ability to detect and interpret magma movements early, the scientific community builds a global framework for early warning systems and disaster mitigation strategies. Mount St. Helens is also becoming a focal point for multidisciplinary collaboration. Seismologists, geophysicists, chemists, geologists, remote sensing specialists, and data scientists are converging on the volcano's developing story, each bringing unique insights. Machine learning algorithms are being used to sift through enormous volumes of seismic and deformation data, identifying patterns that might elude human observation. The integration of artificial intelligence into volcano monitoring is still a growing field, but its potential is clear. Algorithms can process real-time input and forecast changes with astonishing speed and accuracy. Educational initiatives are similarly gaining traction as the volcano enters this new phase. Institutions and outreach programs are leveraging public curiosity to build awareness about volcanic systems and preparedness. Understanding what magma recharge actually means is vital for communities near the volcano. It's not a cause for panic, but rather an invitation to be informed. Teaching people about volcanic timescales, geologic signals, and emergency procedures ensures that, should any future unrest escalate, the public will be ready to respond with clarity and calm. There's also an aesthetic, almost philosophical dimension to this renewed subterranean activity. Mount St. Helens, once rendered desolate and lifeless by eruption, is again harboring a form of creative energy. Magma is the engine of geological change. It births new land, reshapes mountains, and fosters fertile environments once the violence subsides. The mountain is not just recharging in a destructive sense, it is preparing for transformation. Whether or not that transformation breaks the surface in our lifetimes is uncertain, but its beginnings are already written deep within the Earth. From a planetary perspective, Mount St. Helens' reawakening reminds us that Earth's internal dynamics are ongoing and relentless. While we focus on surface phenomena, climate change, urban expansion, ecological conservation, there are titanic processes unfolding kilometers below, with consequences we are only beginning to grasp. The magma rising beneath Mount St. Helens was generated by forces that predate human civilization and will continue long after modern structures have eroded away. This slow-motion drama, unfolding over millennia, speaks to the deep time in which our planet operates. The recharging process also prompts further investigation into regional patterns of magmatism and tectonics. Mount St. Helens is part of a chain of volcanoes stretching from Northern California into British Columbia. Scientists are now examining whether neighboring volcanoes like Mount Adams, Mount Hood, and Mount Rainier are exhibiting similar subsurface activity. While each has its own geological personality, they are connected by deep crustal systems and the same tectonic environment. A change in one may influence stress fields or magma migration in others. Understanding this connectivity is essential to building a coherent picture of volcanic risk in the Pacific Northwest. Satellite constellations are playing an increasingly central role in this effort. NASA's Terra and Aqua satellites, along with the European Space Agency's Sentinel series, are continuously capturing data on surface temperature, gas emissions, land deformation, and vegetation patterns. These systems provide a near-constant stream of observational data, feeding directly into models that update in real time. As new satellites launch with even more sophisticated sensors, the fidelity of these models will only improve, bringing the goal of predictive volcanology ever closer. The cultural and historical context of Mount St. Helens also adds complexity to its ongoing evolution. Indigenous tribes of the region, such as the Cowlitz and the Yakima, have long held the mountain as sacred. Its eruptions, both ancient and modern, are woven into oral histories and traditions that frame the volcano not as a hazard, but as a living entity. In light of the current recharge, there is growing interest in incorporating indigenous knowledge into the broader scientific narrative. These cultural perspectives offer alternative ways of understanding the volcano's rhythms, enriching the discourse with voices that have observed its behavior for generations. Environmentalists and ecologists are also paying attention, not out of fear of destruction, but out of anticipation of how another volcanic episode, no matter how mild, might reshape the landscape. The 1980 eruption created a vast natural laboratory for ecological succession. What was once a barren wasteland became a dynamic, reborn habitat teeming with life. If a future event does occur, it will again offer a chance to observe how ecosystems respond to massive natural disturbances. This is valuable not just for academic study, but for conservation planning and resilience modeling in other parts of the world. Amid all the science and speculation, there's a persistent sense of humility. Mount St. Helens' renewed activity reminds us that human understanding, though vast and growing, still meets its limits when confronting the intricacies of Earth's deep interior. We can measure ground tilt in millimeters and detect earthquakes too faint for human ears, but the final decision to erupt, or not, rests with the mountain. It is a humbling dynamic, one that encourages respect for the planet's power and unpredictability. The ongoing recharging of Mount St. Helens also serves as a mirror for how far geosciences have come. In the years before the 1980 eruption, warning signs were either misunderstood or undervalued. Today, those signs are detected earlier, interpreted with greater nuance, and contextualized within broader geological frameworks. It's a reflection of progress, a testament to interdisciplinary research, technological innovation, and the cumulative nature of scientific discovery. Each new tremor or signal adds to that cumulative effort, pushing the boundary of what we know and what we might soon understand. For young scientists entering the field, Mount St. Helens is becoming a kind of rite of passage, a place to test theories, apply new tools, and engage directly with Earth's dynamic processes. Field camps, remote labs, and graduate research programs are all gravitating toward the volcano, turning it into a hub of intellectual energy. These rising geoscientists are the ones who will carry forward the responsibility of deciphering the mountain's next moves, building upon decades of accumulated knowledge. In the coming years, attention will focus not only on continued magma intrusion, but also on the possibility of thermal anomalies, shallow degassing events, and minor seismic swarms. These will be the next steps in the mountain's reawakening, or perhaps just passing fluctuations in its underground life. Whether the cycle leads to surface activity or subsides into quiescence, it will leave behind a wealth of scientific knowledge, improve hazard modeling techniques, and deepen our understanding of Earth's internal workings. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on magma recharging under Mount St. Helens? Eruption soon or not? We want to hear from you. Thank you for watching and see you next time.